Okay. So hello to one and all present here. Myself Kalpita, and I am the TA of the Transport Phenomena course of NPTEL, and under the guidance of Professor Dasgupta of IT Kharagpur. So we are here with week 4 of the question solving class, and now let us proceed to the first question of the week 4 session of transport phenomena question solving. Okay. So this is the question number 1. This is the question number 1 where if the Prandtl number is greater than 1, what does it signify? Whether it is hydrodynamic boundary layer and the thermal boundary layer develop simultaneously, or the hydrodynamic boundary layer is thicker than thermal boundary layer at a given location, or hydrodynamic boundary layer is thinner than thermal boundary layer at a given location, or hydrodynamic boundary layer does not go at all. Sorry, thermal boundary layer does not go at all. What will be the answer? I'll give you 1 minute to that because it is just one line question, and after that we'll go for the solution. At the last of this class, in previous class, we have not solved one question. That is, one question was left. I've already given you the question, but the solution of that question was left to solve. So today, in the last of this class, we'll be continuing with that question, previous day question. Okay. Okay. So it's been 1 minute, so we will go on with the solution now. So this is class 4. Okay. So what was the question? The question was Prandtl number is greater than Reynolds number, then what does it signify? Okay, so Prandtl number is our viscous diffusion rate upon the thermal diffusion rate. Okay, and the what this, and it is also denoted as momentum diffusivity upon thermal diffusivity. So what does momentum diffusivity signifies? Momentum diffusivity tells us about the material's resistance to the shear flows. That is, different layer of fluid flow with different velocities due to its relational density. For example, speed of the adjacent walls. So in that context, we know that Prandtl number is equal to viscous diffusion rate upon thermal diffusion rate, that is the momentum diffusivity upon thermal diffusivity. That is, Prandtl number is equal to momentum diffusivity upon thermal diffusivity. Momentum diffusivity is mu by rho and thermal diffusivity is K by rho Cp. That is, it is mu Cp by K. So Prandtl number can also be written as momentum, that is hydrodynamic boundary layer upon thermal boundary layer thickness. Hydrodynamic boundary layer thickness upon thermal boundary layer thickness. Okay, so obviously if Prandtl number is greater than 1, then hydrodynamic boundary layer thickness is greater than 1. Thus the hydrodynamic boundary layer develops more rapidly as compared to thermal boundary layer. That is, the answer will be B. Okay. Now let us proceed to the next question. What is the next question? Next question is for next question this will be applied. Okay. So remember this is a Navier-Stokes equation. So for this question, the thickness of the boundary layer delta is arbitrarily taken as the distance away from the surface of the velocity surface where the velocity reaches 99% of the free stream velocity. For the flow of fluid at very low speed and with large viscosity, it is possible to neglect the inertial term from the Navier-Stokes equation. However, for flows at high velocity, small viscosity, it is not always logical. It is not always logical to neglect the inertial term from Navier-Stokes equation. Okay, viscous term from the Navier-Stokes equation. Okay. So answer this. If any one of this line is false, then the whole of this answer will be false. Otherwise, it will be true. So I'll give you 1 minute to answer this, and then we'll go on with the solution. As you can see the question that is displayed, I will give you 1 minute to answer this, and after that we'll go on with the solution. Let me repeat the question for you. The thickness of the boundary layer delta is arbitrarily taken as a distance away from the surface where the velocity reaches 99% of the free stream velocity. For the flow of fluid at very low speed with large viscosity, it is possible to neglect the inertial terms from the Navier-Stokes equation. However, for flows at high velocity and small viscosity, it is not always logical to neglect the viscous term from the Navier-Stokes equation. Now, if any one of these two sentences are false, then mark the entire answer is false. So, this is the question. You can take 1 minute to answer it. Okay, so let us proceed with the solution for the second question. So what does the question tell us about? Okay, so let us first proceed with the Navier-Stokes equation. So the left hand side will be del P plus rho G plus mu del square V is equal to rho dV by dt. For low fluid velocity, all the left hand side will be 0. So for the Navier-Stokes equation, it is small. For the low fluid velocity, everything will be small relative to each other, as we can see for creeping flow. Okay, so but this we can resolve as v vector dot del v vector. This is the viscous term. Okay, so but for low viscosity and high velocity, the product of this velocity and the velocity gradient, that is, that comes in this viscous term, cannot be considered small relative to each other, as there are two velocity terms. So if velocity is high, we cannot we cannot discard this term. So that's why it is, as it's said in the question, it is not always logical to neglect the viscous term from the Navier-Stokes equation, right? Yeah, so yeah, this answer will be true. So the answer is A. Okay, so let us now proceed to question number 3. Consider the two statements. Even if one of them is false, then mark the entire answer as false, or else mark the answer as true. So, similar to the flow of fluids in a pipe, the flow within the boundary layer could be either laminar or turbulent. Furthermore, in a boundary layer, the characteristic dimension is the distance from the leading edge. Leading edge, that is the starting, the edge where the flow starts, edge of the flat plate. And therefore, the calculations for the Reynolds number is not based on the length. Okay. So this is the question. I'll give you 1 minute to come up with the answer. After that, we'll go on with the solution. Sorry. If you have any doubt in understanding the question, do tell. This is rather simple question, Sonu. So as you're in the class, you should answer whether it is true and false. Uh, Either way. Otherwise, we can come up with a solution. You have not undergone the class lecture. Okay. This is the basic lectures. Like, you have not undergone any class, like you have not done any class lecture. This is just the concept of the flat plate. You have done or you have not? I couldn't understand. Okay, then we can come up with the solution. I have other questions also. So once you will attend the question and you will try to solve, then you will be able to understand whether or not you have attended the class. Okay, so what is happening? Just 1 second. Okay, so in a constant diameter pipe, if this is a pipe and the flow is happening from this side, so obviously there will be a hydrodynamic entry length. You understand hydrodynamic entry length, right? Like where the boundary layer won't be fully developed in that region, and after that region, boundary layer will be developed like this. So there will be some distance up to which the boundary layer won't be developed. After that, boundary layer will be developed, but flow will be either turbulent or laminar. It won't be both. But in case of a flat plate, the case is not the same. Like this thing is not the same. Like if flow is coming from this side, suppose this is the free stream velocity u. So Reynolds number depends on x, that is the distance at which we are calculating the Reynolds number, that is u density by mu. So it depends upon the x, the distance from which it is, like we are calculating the Reynolds number. Sometimes it is like here we can get laminar, here we can get transition, and here we can get turbulent, like this will be viscous sublayer and here eddies will be there. So this may happen. So Reynolds number, depending upon the distance from the leading edge and depending upon this velocity, it may change. So we can get on the same plate laminar flow, transition flow, and turbulent flow. So thus, as we can see the second line of the question, in a boundary layer, the characteristic dimension is a distance from the leading edge, and therefore the calculations of the Reynolds number is not based on this length. This is completely wrong. So that's why the answer of this question will be false. So that is answer will be B. Okay. So do you have any doubt regarding this? Okay, sure. So let us proceed to the next question. Okay, so the Blasius steady flow laminar flat plate boundary layer solution of the Prandel's boundary layer equation. In this question, I'll show how the Prandtl boundary layer equation will be developed, and how like Blasius, like I won't be showing the whole solution, but Blasius have solved the Prandtl's equation, and I'll show you what the equations are for heat and for one is the continuity equation, another is Navier-Stokes equation, and one will be the heat equation. So all he have solved to give us the exact solutions. So yeah, involve the definition of similarity parameter based on the simplified form of one-dimensional momentum equation and continuity equation. Okay, so such solutions, the one developed by Blasius, are termed as exact solutions that are and they are available only for limited number of situations. For all other cases, numerical methodologies are usually adopted. Yeah. So answer me this question. I'll give you 1 minute for that. And after that, I'll show you what equations are called the Prandtl equation, and how, like, what Blasius have solved to, like, what equations he have got after solving those equations, Prandtl equation. Okay. So no one have answered, so I'll go on with the solution for now. First, we'll see what the Prandtl equation are. So we'll develop first the continuity equation. So first, we take a body. Here, if this velocity is u, if this is dx and this is dy, this will be u plus the velocity in that direction will be del u del x dx because of this distance traveling. Okay. So, and if v is in this side, this will be v plus del v del y dy. Okay. So, applying law of conservation of mass, what will happen? At steady state, within this control volume, the rate of mass in within the control volume is equal to rate of mass out. If you won't be able to understand anything, kindly stop me and ask the question. Control volume. Okay, this is the simple continuity equation that we have already understood how to derive. So this is 1, like width we are taking as 1. So dy into 1, this velocity from this side, u velocity from this side. So here mass flow rate will be density into the area, cross-sectional area into velocity, right? And that side for v also this is in velocity. For v will be this cos dx, v is entering from dx, is equal to rho into dy into 1 into velocity now will be u plus del u del x dx, this velocity, and plus rho del x into 1 v plus del v del y dy. Okay, so this is rho dy del u del x dx plus rho dx del v del y dy, okay, is equal to 0. So this dy. So this dy will be cancelled out, dx will be cancelled out, this rho will be cancelled out. So this is del u del x plus del v del y is equal to 0. This for 2-dimensional continuity equation. And for 3-dimensional continuity equation, that is del u del x plus del v del y plus del w del z is equal to 0. This is for 3-dimensional. That is del dot v vector is equal to 0. Now, law of conservation of momentum will provide us Navier-Stokes equation. What is Navier-Stokes equation? The algebraic summation of all the forces in a given direction. What are all the forces? This is body force plus surface force. Surface force are that is pressure force, shear force, and body force are gravitational force. Okay, so this is equal to mass into acceleration in that direction. Okay, so Navier-Stokes equation in x direction is rho del u del t plus u del u del x plus v del u del y plus W del U del Z is equal to minus del P del X plus rho Gx plus mu del square U del X square plus del square U del Y square plus del square U del Z square. This is viscous force. This is gravity force. That is body force. This is pressure force. This is acceleration. Okay. This is Navier-Stokes in x direction. Now we will reduce this one. So for 2D, if we consider flow is two-dimensional, so W is equal to 0 and del Z of everything will be 0. So this gives us rho U del X plus V del U del Y minus del P del X plus rho Gx plus mu del square U del X square plus del square U del Y square. This is x direction momentum equation. And another is y direction momentum equation. What is y direction momentum equation? That is density into U del V del X plus V del V del Y is equal to del P del Y plus rho Gy plus mu del square V del X square plus del square V del Y square. Okay. Now, since the boundary layer thickness delta is very small, then length of the plate L, that is delta is far less than L, and flow mainly takes place in x direction. Since the boundary layer thickness is delta is very small as compared to L, thus delta is very small, so we can take as the direction of flow to be x rather than y. So that's why V is far less than U, and this also determines that del V del X is approximately equal to 0, because V is obviously 0, approximately equal to 0. So del V del Y is approximately equal to 0. And obviously the change of U will be in y direction rather than in x direction. Okay, so in y direction momentum equation, if we put above approximation, what we get? Minus del P del Y plus rho Gy is equal to 0. Del P dash del Y is equal to 0, and P dash is equal to P plus rho G plus minus rho G. And P is not a function of Y. That is, P is a function of X. In X direction, since del U del Y is far greater than del U del X, then del square U del X square is equal to 0. Okay, so and the flow is horizontal, so gravity is negligible. So therefore rho gx is equal to 0 in the region above boundary layer, that is the irrotational flow or potential flow, from Bernoulli equation. If we apply in that region the Bernoulli equation, P plus half rho u infinity square is equal to 0, or P is equal to minus rho, del P del x dP dx, let us write it again. dP dx is equal to minus rho du infinity dx is equal to 0. That means del P del x is equal to 0. And that is due to change in u infinity, there will be, due to change in u infinity, there will be no change in pressure force. That is del P del x is equal to 0. And boundary layer is very small, so we can take pressure difference to be small, pressure to not change with x. And above boundary layer, obviously pressure dP dx is equal to 0. So therefore the equation reduces to the x direction momentum equation reduces to del u del x plus v del u del y is equal to nu del square u del y square. This is the x direction momentum equation. Similarly, the energy equation will be rho Cp u del T del x plus v del T del y is equal to K del square T del x square plus del square T del y square plus mu pi double dash. This is the heat. Okay, let's write with something different. This is the heat due to viscous effect. This is due to viscous effect, and for ideal fluid this is 0. This obviously will be 0, similar as velocity. This whole term is the energy transport by conduction, and this whole is the energy transport by advection, that is due to motion. Advection means due to motion. This cancels out because del T del y is far greater than del T del x. Obviously, the change in of temperature in x direction is more as compared to y. So if area is cancelled on both sides, what happens? The final equations are del u del x plus del v del y is equal to 0. This is equation number 1. This is continuity equation. Second equation is u del x plus v del u del y is equal to nu del square u del y square. This is Navier-Stokes equation. This is equation number 2. And equation number 3 is u del t del x plus v del t del y is equal to alpha del square t del y square. This is energy equation. These three equations are equal. These three equations are equal only when nu is equal to alpha. Then these three equations will be equal. So if nu is equal to alpha, that is Prandtl number is equal to 1. So this Prandtl number 1, this was the idea. This equation was solved by Blasius. And Blasius solved it to find the following equation that we already studied. Laminar turbulent. Delta by x is equal to 4.98 by root over Reynolds number. And turbulent is delta by x is equal to 0.369 Reynolds number to the power 1 by 5. And skin friction is equal to 0.664 by root over Reynolds number. And here it is 0.0592 by Reynolds number to the power 1 by 5. Then he solved the third equation, that is the energy equation, solved to get the following results. NUX is equal to HX into x by k. This is Nusselt's number in x direction. 0.332 Reynolds number e to the power half Prandtl number to the power 1 by 3. And another is equal to hxx by k 0.0296 Reynolds number 0.8 Prandtl number 1 by 3. This is for turbulent. This is for laminar. So for laminar, hs is proportional to x to the power minus 0.5, and for turbulent, hx is proportional to x to the power minus 0.2. And from here, he also got delta by delta is equal to Prandtl number to the power 1 by 3. Okay. So if we plot the graph of skin friction and hx, we can get, let me show this also. If this is skin friction and hx and delta. Okay. This is one region, this is one region. Okay, let us use two colors. One is, this is CFX HX proportional to x to the power minus 0.5. This is CFX HX proportional to x to the power minus 0.2. And another one is this is delta x proportional to x to the power 0.8. This is delta x proportional to x to the power plus 0.5. ঠিক আছে, this is x. This is laminar. This is transition. This is turbulent region. Laminar region, transition region, and turbulent. So what is now the answer? Obviously this is true because Prandtl have derived the equation, and Blasius have by giving Prandtl number is equal to 1, Blasius have solved the 3 Prandtl equation to get the solution that I have already showed you. So its answer will be A. That is true. Now we'll go for question number 5. Okay. So let us proceed to question number 5. This is question number 5. So air at 1 atmosphere and 25 degrees Celsius kinetic viscosity is 1.6 10 to the power minus 5 meters square per second. Flows tangential on both sides of a thin, smooth, flat plate of width 5 meter and length 1 meter. The velocity outside the boundary layer is constant at 8 meter per second. Assuming laminar flow, compute the approximate boundary layer thickness at the trailing edge. Okay, so I'll give you 1 minute to solve this, the question that is displayed. Then we'll come up with the solution. If you have any doubt, if you have any doubt, then you can ping me up. If you have any doubt, then you can ping me. Okay, so let us go on with the solution of question number 5. So here it is said that the velocity, the free stream velocity is given as 8 meter per second, right? 8 meter per second. And kinematic viscosity is given as 1.6 into 10 to the power minus 5. And the length at which we need to find out, that is compute the approximate boundary layer thickness at the trailing edge. So the length is 1 meter. It's given, right? So therefore delta, and it is already said that the flow is laminar. So for laminar flow, delta is 5.0 by root over u infinity by nu x. 5 by root over 8 by 1.6 into 10 to the power minus 5 into 1. Sorry. Into 1. So this becomes to be 7.07 into 10 to the power minus 3 meter. So this is 7 mm. So what is the answer? Answer is B. Okay. So let us proceed to the next question. Next question is rather simple. What is the case for the case of unsteady three-dimensional flow? Which of the following is correct general representation of the continuity equation? So this will be the correct representation will be C, right? So next is question number 7. A cylindrical chimney is given of 1 meter in diameter and 25 meter tall. So obviously the length is far greater as compared to the diameter, right? And it is exposed to a uniform velocity of 50 km per hour wind at a standard atmospheric condition. End effects and gust may be neglected, and estimate the bending moment at the base of the chimney due to the wind forces. The values are given. So for this question, we need to find CD at given Reynolds number to find the moment. So to find the CD, this is the graph that you may follow. Okay. So this is the question. After 3 minutes, after 2 minutes, I'll give the graph also. You can now solve. So we'll start up with the solution of this question. Okay, so what is said here that dia is 1 meter and length is 25 meter, right? So in a uniform flow with the velocity of 50 kilometer per hour, right? And pressure is 101 kilopascal, absolute pressure, and temperature is given 15 degrees Celsius. The drag coefficient is given by CD is equal to drag force upon half rho v square into A area. So therefore drag force is equal to CD into area into half rho v square. Since the force per unit length is uniform over the entire length, the resultant force Fd will act at the midpoint of the chimney. What is happening here? The force per unit length is same. In the whole length, the force is uniformly distributed. So it can be Fd can be taken as the midpoint of the chimney. That is all said. So here, cause moment for moment, we need to also give the distance at which the force will be acting. So hence, the moment about the chimney base is moment m naught is equal to FdL by 2 is equal to CD into area into half rho V square L by 2 is equal to CD into area into L by 4 rho V square. Now V is equal to 50 kilometer per hour into 10 to the power 3 meter per kilometer into R by 3600 second. We are just converting V from kilometer per hour to meter per second. So it will be 13.9 meter per second. Okay. So moment is equal to drag force into L by 2. That is the distance at which the distance of action of the moment. And of Fd we can calculate from the drag force. And drag force is equal to this. There is the drag force. This drag force is equal to CD into that we already know, right? So for here at standard temperature pressure, density is equal to 1.23 kilometer per meter kg per meter cube, and mu is equal to 1.79. It is already given in the question, kg per meter second. Therefore, Reynolds number is equal to rho Vd by mu. That is 1.23 kg per meter cube into 13.9 meter per second into 1 meter into meter second upon 1.79 10 to the power minus 5 kg. So this upon this will be 9.55 into 10 to the power 5. So what will be the CD corresponding to this? CD will be, we can see the graph now. CD we can see that in corresponding to that the CD is 0.35 approximately, right? So for the cylinder as for a cylinder as the length that is 25 meter is far greater than its dia that is 1 meter. So the projection area that is AP can be considered to be a rectangle. So AD is equal to DL. Therefore, m naught, that is the moment, is CD area L by 4 rho V square. CD DLL by 4 rho V square. Okay. So CD, okay, this will be 1 by 4 into 0.35 into 1 meter into 25 square meter square into 1.23 kg per meter cube into 13.9 meter square whole square meter square second square into Newton second square per kg meter. Therefore, the moment here will be 13.0 kilonewton meter. This is the answer. Okay. So now we'll go on with the next question. So there is a linked question. So for airflow over a flat plate, the velocity is u and the boundary layer thickness is given as delta. The velocity can be expressed as this equation, and delta is also given. The free stream velocity is 2 meter per second and the air has kinetic viscosity of 1.5 × 10 to the power minus 5 meter square per second, and density is 1.23 kg per meter cube. So what is the question? Choose the closest value of Reynolds number at x is equal to 1 meter. And second question is choose the closest value of fall shear stress at x is equal to 1 meter. One is shear stress, another is Reynolds number. Okay. So I'll give you 3 minutes for this and then we will go on with the solution. And then we'll go on with the solution. Okay. Okay, so let us start with the next question solution. So question number 8 first. Okay, so we need to first find out the Reynolds number. Density is given as 1.23 kg per meter cube. Nu is given as mu by rho as 1.5 into 10 to the power minus 5 meter square per second. Velocity given 2 meter per second. X and L given as 1 meter. Reynolds number rho u L by mu is equal to 2 into 1 upon 1.5 into 10 to the power minus 5. This is meter per second into meter upon meter square per second. This is 1.34 into 10 to the power 10 to the power minus 5. Sorry, 10 to the power 5. 10 to the power 5, 5 into 10 to the power 5. This answer is B. Okay. Question number 9 is now shear stress is tau naught is equal to mu du dy y is equal to 0. Small u by capital U is equal to 3 by 2 y by delta minus y cube by 2 delta cube du dy is equal to capital U 3 by 2 delta 3y square by 2 delta cube. Okay, so we need to find out du dy at y is equal to 0. Du dy we already found out, so hence du dy at y is equal to 0 is equal to 3 by 2 capital U by delta. So, and it's given that delta is equal to 4.64x upon Reynolds number. Reynolds number half is equal to 4.64 into x by root over rho u x by mu. So putting x is equal to 1, we get delta at x is equal to 1 is equal to 4.64 upon root over 2 into 1 by 1.5 into 10 to the power minus 5 is equal to 0.0127 meter. Therefore, tau naught is equal to mu du dy is equal to 3 by 2 mu u by delta is equal to 3 by 2 nu rho u by delta is equal to 3 by 2 into 1.5 into 10 to the power minus 5 into 1.23 into 2 by 0.0127. That is tau naught is equal to 4.355 into 10 to the power minus 3 Newton meter square per meter square. This is A. Answer is A. Okay, now let us proceed to question number 10. An incompressible fluid flows over flat plate with zero pressure gradient. The boundary layer thickness is 1 millimeter at a location where Reynolds number is 1000. If the velocity of the fluid alone is increased by a factor of 4, then choose the correct value for boundary layer thickness in mm at the same location. So I'll give you 3 minutes again to solve this, and then we'll go on with the solution. So solution of this question will be Reynolds number is given as 1000. That is less than 5 in 20 power 5 for flat plate. So obviously the flow is laminar. As we already solved another question today like this. So for laminar flow, delta upon x is equal to 4.98 upon Reynolds number, root over Reynolds number. And Reynolds number is equal to L V rho upon mu. Reynolds number is proportional to V. That is delta is proportional to Reynolds number minus half. So delta 2 by delta 1 is equal to root over RE1 by RE2. That is root over V1 by V2 because Reynolds number is directly proportional to V. So delta 2 upon delta 1 is given as 1. Delta 1 is given as 1 mm. Yeah, 1 mm. Okay. So root over V by 4 times of V. This is given. So delta 2 is 0.5 mm. So answer is C. Now question number 11. So what is the question number 11? Okay. During the analysis of laminar boundary layer over flat plate, the skin friction is inversely proportional to the square root of local Reynolds number, and the dynamic viscosity and the area viscosity are both properties of fluid. Answer whether it is true or false. I'll give you 2 minutes for this. Okay. So in this, the first thing that is written is in flat plate in laminar boundary layer. The skin friction is inversely proportional to the square root of the local Reynolds number. This is true obviously because we know the skin friction is equal to point for laminar flow 0.664 upon root over Reynolds number. Okay, so that means CFX is directly proportional to 1 upon root over Reynolds number. So the first one is true, but the eddy viscosity in case the dynamic viscosity, eddy viscosity, both are properties of fluid. No, the eddy viscosity is a coefficient that is relating average shear stress within a turbulent flow of water or air to the vertical gradient of velocity. The eddy viscosity depends on the fluid density and the distance from the river bed or the ground surface. Eddy viscosity is primarily decided by the conditions of the flow. But for dynamic viscosity, it is the property of the fluid. So eddy viscosity is not the property of fluid. So that's why this answer is false. Now, that is B. Okay. So now let us go on with the question, the last question of today's class. That was the last question of the previous class too. So we were supposed to solve this one. This is a big question and we have 15 minutes to do. So I'll give you 3 minutes to solve this, 4 minutes in fact to solve this, then we'll go on with the solution. So consider a fully developed flow and a pressure driven flow in a of a neutron fluid in a sufficiently long annulus of radius r and kappa r. So the flow is in the annulus region between kappa r to r, where kappa is less than 1. For the zero gravity, the general solution of the uz is given. So we need to find the velocity profile, the shear stress, the maximum velocity, volumetric flow rate, and the average velocity. Okay, this is the question. So your time starts and to come up with a solution, and then we'll go for the solution ourselves. Okay, let us now proceed with this solution. Okay, first uz is given as 1 upon 4 eta del p del z r squared plus c1 ln r plus c2. We need to find uz maximum, q, and uz bar, that is the average velocity. The boundary conditions are uz is equal to 0 at small r is equal to kappa r, and uz is equal to 0 at small r is equal to capital R. Now putting the boundary conditions in the main equation, in this equation, we get 0 is equal to 1 by 4 eta del p del z kappa square r square plus c1 ln kappa r plus c2. This is equation 1. And another is 1 by 4 eta del p del z r square plus c2 plus c1, sorry, plus c1 ln r plus c2. This is equation 2. 2 minus 1 will be r square 4 eta del p del z 1 minus kappa square plus c1 ln 1 by kappa is equal to 0. Okay, so c1 is equal to minus 1 by 4 eta del p del z r square 1 minus kappa square by ln 1 by kappa. C2 is equal to minus 1 by 4 eta del p del z r square plus 1 by 4 eta del p del z r square 1 minus kappa square ln r by ln 1 by kappa. This is this in this region only, minus r square by 4 eta del p del z 1 minus kappa square ln r by ln 1 by kappa. Okay, so this is C2. So putting everything in uz, we get uz is equal to 1 by 4 eta del p del z r square minus 1 by 4 eta del p del z r square 1 minus kappa square by ln 1 by kappa, and here ln r will also be there. So this is 1 minus another thing is there, that is left, that is C2, minus r square by 4 eta del p del z 1 minus kappa square ln r by ln 1 by kappa, minus 1 by 4 eta del p del z r square 1 plus 1 minus kappa square ln 1 by kappa minus ln r plus ln r plus small r by capital R whole square. Therefore, uz is equal to minus 1 by 4 eta del p del z r square 1 plus small r by capital R whole square plus 1 minus kappa square by ln 1 by kappa ln small r by capital R. So therefore tau r z, now shear stress, is equal to minus eta del u z del r. So this is 1 by 4 del p del z r 2 small r by capital R minus 1 minus kappa square ln 1 by kappa capital R by small r. Okay, so the maximum velocity occurs at the point where tau rz is equal to 0, equivalent to duz dr is equal to 0. Thus tau r Thus tau rz is equal to 0. 2 small r by capital R is equal to 1 minus kappa square by ln 1 by kappa capital R by small r. So R star is capital R 1 minus kappa square by 2 ln 1 by kappa half. This putting this in expression of uz, we get uz maximum. This is r at which the maximum velocity is there. So maximum velocity is minus 1 by 4 eta del p del z capital R square 1 minus 1 by r square 1 minus kappa square by 2 ln 1 by kappa plus 1 minus kappa square ln 1 by kappa ln r square 1 minus kappa square by 2 ln 1 by kappa half, not square, sorry, this is r. Okay. Okay, so this r and r will be cut off. Okay, after that this is minus 1 by 4 eta del p del z r square 1 minus kappa square by 2 ln 1 by kappa, then 1 minus ln 1 minus kappa square by 2 ln 1 by kappa is equal to uz max, or uz max is equal to minus 1 by 4 eta del p del z r square 1 minus kappa square by 2 ln 1 by kappa, here 1 minus ln 1 minus kappa square by 2 ln 1 by kappa. Now volumetric flow rate Q is equal to kappa R to R, because flow rate will be in the concentric in the annulus region only. So from kappa to R, user 2 pi R dr. I won't be solving everything. User just need to put here the value of user, that is 2 pi R minus 4 eta del p del z r square 1 minus small r by capital R whole square plus 1 minus kappa square ln 1 by kappa ln small r by capital R. This is dr. So this becomes Q becomes as minus pi by a theta del B del Z r to the power 4 1 minus kappa square, sorry, kappa to the power 4 minus 1 minus kappa square whole square by ln 1 by kappa. Now average velocity u z bar is equal to q upon pi capital R square minus pi kappa r whole square. This is equal to minus pi by a theta del B del Z r to the power 4 1 minus kappa to the power 4 minus 1 minus kappa square whole square by ln 1 by kappa. This is, we can write as 1 minus kappa square 1 plus kappa square. So this is upon pi r square 1 minus kappa square. So this minus kappa square and this 1 minus kappa square and this 1 minus kappa square cancels out. So this becomes as pi by a theta del P del Z r to the power 4 1 minus kappa square 1 plus kappa square minus 1 minus kappa square by ln 1 by kappa. Okay. Upon pi r square 1 minus kappa square. This to 1 minus kappa square. So this already cut off r square. This cuts off. So u z bar is equal to becomes 1 by a theta r square del P del Z 1 plus kappa square minus 1 minus kappa square ln 1 by kappa. This is the answer. Okay, so this is all about this class. So we are ending the class here, and I'll see you guys next week.